Everyone, you're welcome. This is Shadows Academy. You're welcome to my channel. It's a channel for maths and physics. So please click on the link below. Like and subscribe. Please like and subscribe. Thank you so much. Shadows Academy. You're welcome. This is Shadows Academy, and today we are actually going to be taking a look at sequence in mathematical analysis. So our goal is actually to understand what is truly the convergence of a given sequence. And remember that when we are talking about mathematical analysis, we're talking about a field of mathematics that the basic idea is the concept of limits. So let us quickly see what does it mean for a sequence to actually what? Converge. We have a definition, as you can see on the board. Let Xn be a sequence, a given sequence, and let A be a fixed real number. Then for Xn, which is a sequence, to converge, we say Sn tends to the limit A as n tends to infinity. So the point of convergence of the sequence is for our terms in the sequence to actually approach a definite real number. And as we can see, this is the symbolic representation that as you go further in the terms of the sequence, n tending to infinity tells us that we are progressing in the terms of the sequence. The first term, second term, third term to the nth term, as we go forward even to infinity, then we have our sequence approaching a definite real number. So whenever this occurs, we say that the sequence is convergent. So a convergent sequence is actually a sequence whose limit is actually what? Defined. That is the basic idea of the convergence of a sequence. So the concept of limit is the basis for defining the convergence of a sequence. So we'll continue on the convergence of sequence. This is Shadows Academy. How to know that this real number A is the limit of the sequence Sn. Now we have defined the convergence of the sequence Sn as meaning that Xn has a limit which is what? A. As n tends to what? Infinity. But how do we mathematically prove this? That the real number A is actually the limit of our sequence Sn. We need to look at this definition. There are mathematical conditions in this definition that if those conditions are shown to be satisfied, then we say that that real number A is actually the limit of our sequence Sn. For every real number E greater than 0, which we can call our epsilon, it's choosing to be so small, but it must be a number that is actually greater than what? 0. Now, there exists a natural number n. We can find a natural number such that for every natural number, small n, that is greater or equal to that natural number we found, this condition is satisfied. So when the condition epsilon greater than 0, n greater than or equal to capital letter N, and then this third condition, if these three conditions are satisfied, then we say that the real number A is actually the limit of our sequence Xn. So we have here that it actually measures how close our sequence is to our limit. How close? how close it is to our limit. The value of e, as we say, must be a real number that should be greater than 0, but then a very small real number. And symbolically, we can see here that for every epsilon greater than 0, there exists a natural number n, such that for every natural number greater or equal to the natural number n, which actually depends on the epsilon, then we have that the absolute value of the difference between the sequence and the limit must be less than or equal to the epsilon. So whenever a problem is given for us to show that a particular real number is the limit of a given sequence, all we need is to establish mathematically that these three conditions are satisfied. 1, 2, and 3. So if we are able to show that these three conditions are satisfied, then we have been able to prove that that real number is actually the limit of our sequence. Basically, the approach is to start from this, the absolute difference of the sequence and its limit. When we start from this, we can, from this, then arrive at this expression under the condition that our epsilon is greater than 0. Once we find that real number, once we find that natural number that is greater or equal to this natural number that depends on epsilon, then we have established the proof. Now I'm going to type everything up on the definition of the concept of the convergence of the sequence by using this particular example. So I want you to be attentive to this. This particular example is going to bring together everything that I've been saying earlier. Once again, this is Shadows Academy. So we have given the sequence. These are sequences defined as this. Now we are asked to prove that the sequence actually converges to the real number 4. And then the second part of the example is for us to prove that the sequence does not converge to the real number 2. So let's see how this works. Remember I said that when you want to establish that a limit is actually, that a real number is actually the limit of a given sequence, you need to establish those mathematical conditions. So I start with the first one. Another way to write this question is to say that lim of xn as n tends to infinity is 4, where our Sn definitely has been defined as 4 plus 3 over n. So what we are saying is that we want to actually show that the real number 4 is the limit of this sequence. So the first thing to do is to always start from this condition, that xn, the absolute value of the sequence, the difference of the sequence and the limit, the less than equal to the epsilon. So we have from here, we can say that 4 plus 3 over n minus 4 is less than or equal to the epsilon. So these are sequence and these are limits. This is the absolute value is less than or equal to this. So this is the first condition. Now we are going to now use this condition by series of mathematical arguments, which is the basis of mathematical proof, to now establish that there is a natural number that will be greater or equal to that given natural number that depends on the epsilon. So we have here 4 cancels 4. You have 3 over n absolute, which we can remove the absolute to have this, of which if we make n the subject of the formula, we have n greater or equal to 3 over epsilon. So here we are saying that our natural number, we have found it to be greater or equal to 3 over epsilon. Now, watch this. Remember that if epsilon is greater than what? 0, and epsilon is a real number. So we can actually find a real number which is greater than 0, which if we make a substitution here, then we can show that n is actually we can show that this expression is actually a natural number for which n is greater or equal to. So we can actually find an epsilon. We can say let our epsilon be 1. 1 is greater than 0. And if you say 3 over 1, you have 3, which is actually a natural number. So n is greater or equal to 3, which is actually satisfying our earlier condition. So that tells us that 4 is actually the limit of our given sequence. Now let's see the second one. We want to show that the limit of the sequence is not 2 as n tends to what? Infinity. Once again, we start with our condition that xn minus a less than equal to this. Then we have, okay, let's move forward. We have, let me divide this. Then we have 4 plus 3 over n, which is our sequence minus the limits less than or equal to epsilon. So when we do this computation, we have 2 plus 3 over n, then we have less than or equal to epsilon. So we take the absolute value, let's take the absolute value to be 2 plus 3 over n less than or equal to epsilon. So when we do this, we can make n the subject of formula by having 3 over n less than or equal to epsilon minus 2. Then we have n is greater or equal to 3 over epsilon minus 2. So this is the natural number that we are able to find when we are trying to show that 2 is not the limit of this sequence. Now let us reason, let us interpret the conclusion to see whether actually 2 is not a limit or a limit. Now remember we say that epsilon should be greater than what? 0. Now, if you choose a real number greater than 0, look at this expression very well. You discover that there is actually a real number that is greater than 0. That when you substitute in this expression, you will get a number that is no longer a natural what? Number. Let's say we choose 1 for example. So 1 minus 2 is minus 1. 3 over minus 1 is minus what? 3. Which does not satisfy that n is actually a natural number. Remember in that definition, we made a statement that n is actually a natural number. So this does not justify it. So that tells us that 2 cannot be the limit of that sequence.